So this is always a little bit of a puzzle for me. How do you deal with those massive particles? If there was a massless charged particle, you might imagine it decays into that. But there aren't any, so that doesn't work. However, it could be the case, and this is the position which I'm holding to here, that mass is not such an absolute constant as we think of it as. In present-day physics, it is, but it may be that the physics where we take into account, for instance, the cosmological constant. I haven't actually mentioned that yet, except that I should have, because when I talk about this exponential expansion of the universe, as I had on the transparency which I started to talk off with, this one here, the accelerated expansion comes about, well, people refer to it as dark energy and all sorts of mysterious terms like that. I think I'm just going to call it the cosmological constant. This was a term that Einstein introduced in 1917 to amend his original equations for what turned out to be the wrong reason, because he wanted a universe which was static, not expanding, and then when he became persuaded that the universe actually was expanding, he regarded the introduction of this term, what's called the Landau term, he regarded that as his greatest mistake. However, it turns out that even Einstein's great mistakes are sometimes true. But this one here apparently is true. It might be something else other than the cosmological constant. It seems that the best explanation for this expansion, this accelerating expansion, is that there is this term, Einstein's equations, that it's positive, and I'm accepting that. I say that there is a positive cosmological constant. This has the character that the infinity of the universe, as I call it, is what's called space-like. If there weren't a cosmological constant, it would be tilted up at 45 degrees, and the more I'm going to say would work. But if you have the positive cosmological constant, then it turns out to be space-like. So I have the lambda that is zero. Now, I'm just saying this is a mathematical trick here. What was I going to say about cosmological constant? Yes. If you describe your particle physics in terms of what people often do, representation theory, or called the Poincare group, and the symmetry group of local physics. But if you have a cosmological constant, this symmetry group is slightly different. It's what's called a de Sitter group. And the thing about the symmetry group, the Poincare group, where you don't have a cosmological constant, you have things called Casimir operators, which are, in effect, the mass and the charge, the mass and the spin. And mass and spin are supposed to be absolute constants for stable particles. But if you have a cosmological constant, it may be that they're not absolute constants. And so I'm playing with this idea here and saying that maybe that allows the mass to fade away. So we're talking about a long time, blue ball years and longer than that. We're talking infinite time, in fact. So could it be that the mass does in fact fade away? I'm not saying that the particles decay into a massless particle. I'm saying that they become, in the infinite limit, massless. So that the mass is not quite the constant we think of as. Well, don't worry too much about that. The main idea is that here we have this boundary that somehow is infinity as far as we're concerned, but as far as photons are concerned, it's not considered to be infinity. I've drawn the picture here. They're kind of squashing down of infinity to a finite region. Now I'm going to do something to the other end, which is somewhat complementary to that, which has to do with this, the second law of thermodynamics, the problem about the very special nature of the Big Bang. Now the Big Bang, come back to this first. I should say there are theorems, primarily the Helmholtz-Friedrich, some very good results that tell us that the general sort of situation, if you don't have any mass running around at the end, the general situation is that you will get a smooth boundary. So from the point of view of the conformal geometry, or Laplacian geometry, you could imagine extending this space-time to beyond infinity. It looks as though it would make mathematical sense. It's a mathematical trick, if you like, but it would make mathematical sense. Now, I'm going to do something on the other side, which is to incorporate the huge constraint that appears to have been put on the Big Bang at the beginning. And if you go into numbers, you find it's absolutely enormous constraint. Something like 1 part in 10 to the power 10 to the power 124 for all the observed material in the universe. I won't go into the reason for that figure at the moment, but it comes from the Bekenstein-Hawking formula for black hole entropy. And there is a potential for black holes to form and get bigger and bigger, and that's where this number comes from. So the question is, reversing time, which I was doing over there, why is it that those much more complicated degrees of freedom, when the gravitational degrees of freedom are not constrained to be zero, how do we understand that? Well, I call this a Weyl curvature hypothesis for a long time. It's simple. Weyl curvature measures the type of curvature that describes gravitational degrees of freedom. I don't particularly want to go into that description here, because Paul Todd has another way of putting it, which is much nicer, geometrically nicer, than talking about this Weyl curvature. It expresses the same sort of thing. But his idea is to say that the particular constraint on the Big Bang that would give us the sorts of things we see would be that you can stretch out infinity, as I've actually done in that picture over there, to, again, a smooth surface, which you could imagine extending to the floor. Now, the trick here is not that everything fades away and you've got nothing left which has any mass, but that when you get close to the Big Bang, temperatures get so large that the rest mass energy becomes completely irrelevant. You have to get temperatures larger than the energy of the Higgs particle, if there is one. The sorts of ideas which seem to be involved in present-day particle physics suggest that higher than a certain temperature, you would basically lose the concept of mass. And it's very reasonable to suppose that the dominant physics going on is, again, physics which is conformally invariant. So the mass becomes irrelevant, and then the particles, more or less, you don't know that the scale is there. They're interested only in the light cones, and the geometry is the conformal geometry again. And the Todd proposal is to say, as now a condition on the early universe, which is that you can extend to prior to the Big Bang in a smooth way. So here I've incorporated in this picture both things. The infinite compression in the future, which is something which more or less happens automatically when you have a cosmological constant, which is positive. Positive cosmological constant and material which becomes massless in the infinite future. This more or less happens automatically. The fact that you can stretch this out to a smooth boundary is a huge constraint in the beginning universe, but it's a constraint which seems to be in accordance with what we see. That the gravitational degrees of freedom are set pretty well to zero, and everything else is allowed to roam as infinite as it likes, or so yeah, that's the picture we have. Now I'm going to go a little further than that, not just saying you can do that trick, but what I do further is to go back to my earlier picture here, and suppose maybe you could go on. Now I'm not saying that this is our universe, and this is our universe. This has problems, if you want to join those together. There are problems in principle which I'd rather avoid. So I'm not saying that. I'm saying that this is, if you like, our eon. This is our Big Bang. And this is the remote future of a previous eon. So that's the scene. I'm joining them together. And that means that in this picture here, we have an eon prior to ours and an eon post ours. And here we go. And as far as I have no reason to suggest that these don't continue indefinitely in both directions. You could imagine that they evolved in some way, or perhaps not, but that's not what I'm saying. I'm supposing that this is something which just continues indefinitely. There was no actual beginning. It's very much like the old steady state model in a certain sense. Philosophically, it's like that the universe was always there in a certain sense, and what it's doing now is very much governed by what it did in the previous eon. And the whole thing settles down into some sort of steady progression that keeps on going like this. So that's the picture. It's what I call conformal cyclic cosmology. It does all sorts of things. It solves problems, and it creates problems, and that sort of thing. I suggested we think about here what to do with extremely low entropy in the gravitational degrees of freedom. Details departures from uniformity and so on, that's conformal cyclic cosmology, and so on. Now, one thing that's very different from standard proposals, I mentioned that quantum gravity is usually invoked, or when people talk about inflation, it's the quantum fluctuations in the infantile field, both to give you the irregularities in the universe that we see. This is something completely different, because according to the other schemes, one has quantum mechanics entering into the picture in a fundamental way. Here, you get away from it. You say that it's classical equations which will govern the way you go from one to the next. I don't know how much time I'm going to have today. I was hoping to indicate something of these equations, which I will do. I have to rattle through them rather quickly, but that is the idea, is that there are equations which enable you to carry through from one eon to the next. And as far as I can see, they're completely determined. Okay, quantum effects will be present, but they're not actually showing themselves at the crossover in a very strong way. And certainly not like in other schemes, where you have either quantum gravity governing somehow what's going on in the early universe, or you have these quantum fluctuations in the interton field, if you have inflation and so on. And these schemes, you don't really know what's going on, that's the trouble. Whereas here, it's very tight. And the evolution is something which you could evolve using classical equations without very much freedom in how you monkey with the equations. They're pretty well fixed. Let me see, I've got one here. Some people might say, surely near the Big Bang, space-time radiation is down to type plane. This is what my quantum gravity friends are saying, see? So the quantum flow, space-time chaos, discrete space-time, testing all kinds of geometry might happen. Well, I'm saying that these would happen in black hole singularities where this just doesn't work. Black hole singularities, yes indeed. You've got curvatures becoming infinite. The point here is, yes, again you have curvatures approaching infinity. The radii curvature get down to what's called the Planck scale, where you would expect to see space-time behaving in all sorts of extraordinary quantum ways. That may happen in a kind of black hole, but the Big Bang, the point is here that it's the Bayer curvature which would have to go down to the radii Bayer curvature, go down to the Planck scale, and that doesn't happen here. It's only the Ricci curvature which becomes infinite, and the Ricci curvature is just something you can scale away with this stretching. So that's the idea. You have no Bayer. Some of the things I'm saying are more to these people, experts who know about these things. Now, let me refer to two issues. One of them I'm going to refer to rather quickly, and it's an important issue. And this is, you might worry, from what I've been saying earlier, about entropy increasing. And if entropy is increasing all the time, why isn't that still working here? So you'd expect that the entropy is going up and up and up, randomly going up and up and up. And how can that be consistent in a picture like this? Well, this was one of the things that worried me for a fair length of time, thinking maybe that phase space measures get rescaled or something, but that doesn't really work. Let me give you what I think the answer is. And this has to do with, again, to do with the Hawking evaporation, which I've got down at the bottom. This is a conformal diagram, which I have to explain, so let's not worry too much about it. But let me talk about the picture here. The idea is, when a black hole disappears at the top, as it's doing down here, it swallows information. Now, this is a thing called the information paradox, and lots of physicists have worried about that, including Stephen Hawking, who originally put forward the idea that information is destroyed in a black hole, and I think he was right, originally, that it is destroyed. Now, a lot of physicists these days, because they consider that information can't be destroyed in a quantum process, that it would have somehow to be recovered outside in some subtle way. I just find that very hard to believe, especially because when we get close to the singularity, you can